Okay, Giancoli 4.5, 4.6. Newton's third law. So anytime a force is exerting on an object, that force is caused by another object. So, for example, you chop your hand onto a desk, as you see here. The force you exert on the desk will be equal to the force that the desk exerts on your hand. But it's equal force, but opposite direction. So equal force, opposite direction. So whenever one object exerts a force on the second object exerts an equal force in the opposite direction of the first force. So forces are equal and opposite when they are applied by one object to another. And the big thing is this: the forces are exerted on different objects. So they're not acting on the same object. So like in this case, you have a skater that's pushing off of the wall. The skater's applying a force to the wall, but the wall is now applying a force to the skater. So you can see that the two forces are equal, but in opposite directions, and they're on different objects. Rocket propulsion also is explained in the third law. So when a rocket takes off, hot gases and from the combustion, from the burning of the fuel, come out of the tail at high speeds. Once the gases shoot out, this high speed of gases shooting out then leads to the rocket being propelling upward. Now, here's the big one. The rocket does not need anything to push against. So this rocket is launching, even though it's on a container. The gases aren't pushing off of something to launch it. It's the gases shooting out cause an equal and opposite force to cause liftoff. And when we can take those two forces, it's the same. So the same force required to lift the rocket is equal to the force of the gases shooting out of the tail, or of the fuel chambers of the spaceship here. So equal and opposite. When we look at the third law, we have this kind of notation, right? So in this case, this lady's walking on the ground. So she's putting force of the person on the ground. Okay, so that's PG, and then the force of the ground on the person is GP. So you're switching the letters. So person on the ground, ground on the person, and then the forces are the same, just that one's going to be negative while the other one's positive. And again, the idea of positive and negative is based on what you want it to be. In this case, they're saying right's negative and left's positive, which is fine. But this is how we kind of designate it when we talk about the third law. So what exerts the force to move a car, and what makes a car go forward? So this is kind of a tricky question. The force to move a car comes from the engine. The engine, by combusting gas, that's where it comes from. Now, to make a car go forward, it has to be, that energy then has to be applied to the tires, and so as it works its way through, and the tires push against the ground. The tires push against the ground pushes back on the tires, and that's what forces the car to go forward. So it's the force of the tires in the ground going against each other. Michelangelo's assistant has been assigned of moving a heavy block of marble using a sled. And this is what he says to his boss. When I exert a forward force on the sled exerts an equal and opposite force backward. So how can I ever start it moving? No matter how hard I pull, the backward reaction force always equals my forward force. So the net force must be zero. I'll never be able to move this load. Is he correct? Well, in a simple sense, yes, he is correct. But in reality, let's look. So to pull this marble, the force of the assistant on the ground has to be there, right? And so the force of the assistant on the ground is the force that the assistant applies. This assistant on the sled is going to be by the string, and that's a tension force, so it's equal all the way through. The force on the ground exerted by the sled and the frictional force of the sled and the ground are also going to be equal when the thing is stationary. The goal is, if you can get this force greater than friction, you can propel it forward. And to get this force greater than friction, it's all about how hard the assistant pushes on the ground. So yeah, I mean, in a simple sense, maybe he's correct, but in reality, there's a lot more to it in this diagram to get this piece of marble to move. And that's, if you want to make it move, you just got to make this force, right? The force that you're applying here has to be greater than this force. And if that's the case, you're going to make this thing move. A tennis ball collides head-on with a more massive baseball. Which ball experiences the greater force of impact? Which experiences the greater acceleration during the impact? And which of Newton's laws are useful to obtain the correct answers? Well, which ball experiences the greater force of impact? The forces are the same, equal and opposite. Which has the greater acceleration? Well, that goes back to Newton's second law, F equals ma. Since the baseball has more mass, it's going to have less acceleration during impact than the tennis ball. The forces are equal. Masses are different. So the more massive object will have less acceleration. So the tennis ball will have the greater acceleration because it's less massive. So we need the third law and the second law to do that. And that's your answer to part 3. Part D, if you push on a heavy desk, does it always push back on you? And the answer is B, yes, for sure. It's just if you want it to move, you have to apply more force to the ground to get that thing to move. Weight, the force of gravity and the normal force. Weight is the force of gravity of an object exerted by gravity. Force of gravity is equal to mass times g. G is where you're at on Earth. It's 9.8. An object at rest has no net force acting on it. So if it's sitting on a table, gravity's still pulling it downward. What's holding it in place? So there has to be a force that holds something in place because gravity is always acting on our objects. And we call that force the normal force. So normal force pushes up and it counteracts gravity. So what happens is if the object's sitting on a table, the forces are balanced. So normal force and gravity are equal. If one of these forces is too big, so if the force downward, so if gravity is greater than normal force, obviously we're going to break through this this table and have other things happening, right? But that's why something sits still, is the normal force that counteracts gravity on a sitting object or on something on a flat surface. If it doesn't accelerate up or down, gravity has to be counteracted. Weight, normal force in a box. A friend has given you a special gift, a box of mass 10 kilograms with a mystery surprise inside. The box is resting on a smooth, horizontal surface of a table. A, determine the weight and normal force. B, now your friend pushes down the box with a force of 40 newtons. Again, determine the normal force exerted on the box by the table. And C, if your friend pulls upward on the box with a force of 40 newtons, what now is the normal force exerted on the box by the table? Do it now. Okay, so weight, normal force in a box. So I read through this already in the video, but so we're going to determine the weight of the box and the normal force by the table. So that's A, okay? So as we know, the force of gravity is weight, and it's m times g, and that's going downward. So if I take 10 times 9.8, that equals 98 newtons going down. Now, since the box itself sitting on the table is not accelerating, forces are balanced, which means my normal force is going to be equal but opposite. So this is 98 down. This one's going to be 98 up. So my normal force in A is going to be 98 newtons. But now let's say that our friend decides to push down on the box. So pushing down with the force of 40 newtons. So now I got to take a look at this and go, okay, so I have a force of gravity on this that's still 98 newtons, but then I'm pushing down with 40. So both forces going down, so my downward force is 98 plus 40. It's 138 newtons. So 138 newtons going down. Now once again, I'm pushing down, but the box still isn't moving, which means that my upward force, or normal force, has to counteract that. So it's going to be equal but opposite. 138 newtons going upward. Now the last case. Again, now we're pulling up on a string, or pulling up on it at 40 newtons. Again, going downward, the force of gravity is 98 newtons. 40 newtons going up. What is the normal force acting on the box? So going down is 98. That's going to equal 40 newtons that I'm pushing up, plus whatever normal force there is are going to be equal but opposite. So I'm going to solve for my normal force, and my normal force is going to be 58 newtons. So because the box isn't moving or isn't accelerating, then my forces are balanced, and I just have to add my forces up that are going down and make them equal my forces that are going up, and then I can solve for any unknowns that I have. Accelerating a box. What happens when a person pulls upward on the box in the previous example with a force equal to or greater than the box's weight? So, for example, let's let the force of pull be 100 newtons rather than the 40 newtons. Okay, do it now.
Okay, so now we're looking at the same box from before. Box is sitting on a table. We know that the mass is 10 kilograms, so the force of gravity is 98. But then we're going to pull up on the box, either with a string or with our hands, with a force of 100 newtons. Now, right away, we see our forces aren't going to be balanced anymore. Once we pull up, obviously there's no more normal force because the force to pull it up is going to be greater than the force of gravity. So there's going to be no more normal force. So the question is, what's the box going to do? Well, our forces are going to become unbalanced, which leads me to this equation, Newton's second law. The net force is equal to mass times acceleration. So what's my net force? My net force is the upward force of 100 added to my negative 98 newtons here is equal to ma. 100 minus 98 is 2 newtons. The mass is 10 kilograms. And I solve for a. So I divide by 10. My acceleration is 0.2 meters per second squared. So net force is the difference between the forces. And that's equal to mass times acceleration. So if I know the mass, I can find the acceleration. If I knew the acceleration, I could figure the mass, even though that you don't do that a whole lot. But I can find out how much this is going to accelerate by knowing the differences in my force.
And apparent weight loss. A 65 kilogram woman descends in an elevator that briefly accelerates at 0.20 g downward. She stands on a scale that reads in kilograms. A. During this acceleration, what is her weight and what does the scale read? And B. What does the scale read when the elevator descends at a constant speed of 2 meters per second? We'll look at this and kind of explain some of these elevator problems so you can get a sense as to what this changing acceleration actually means, okay? But normal force is the scale, and your weight, and the force of gravity is your actual weight. Do it now.
All right, so the elevator problem, okay, where you're standing on a scale, and we want to know that during the acceleration, what is her weight and what does the scale read? So on a scale, what happens is this. Gravity's pulling you down. Okay, that's the force of gravity, which is mass times g. The scale pushes back up, and then what you read in the scale is actually the normal force. So that's the weight on the scale, all right? And if we're not moving at all, okay, when we stand on this, since we're not moving or accelerating, this and this are equal. So our weight should equal the normal force, is what we expect. So the weight on the scale will equal our force of gravity. So let's say that our person here is 65 kilograms. 65 times 9.8. We know that the weight on the scale is going to be 637 newtons, okay? Which is the same as her weight. So we can see how the scale would work. But now let's say we get on an elevator. And on the elevator, we start to accelerate downward, 0.2 g. So let's say that our acceleration is 0.2 times 9.8. So 1.96 is going to be our acceleration going downward. Now we have to think about what the scale is going to actually read, okay? Because when they're balanced, when we're not moving, it's going to be the same. But if we accelerate downward, what's it going to read? Is it going to read more or is it going to read less? So let's take a look at this problem using the second law. So net force is mass times acceleration. We know our acceleration, right? And we know our mass. So what we want to find is what our normal force is going to be. So again, you got to pick a positive, negative, and I'm going to make up positive, down, negative, okay? So my net force is going to be normal force minus mg, or the force of gravity, and that equals ma. Normal force is going to be what the scale reads. My mass is my weight is 637. So normal force minus 637 equals ma. My m is 65. But now my acceleration is going down, so my acceleration is negative 1.96, okay? And now I can work some math here. So I take 65 times negative 1.96, negative 127.4 newtons, minus 637 newtons, Fn. If I add 637 newtons to each side, the normal force is plus 637, 509.6 newtons. So the scale is going to read less than my actual weight when I'm going down in an elevator. And if you do this on an elevator, you see the same thing as long as you accelerated fast enough to get a reading. Elevator out here doesn't do that, and we've tried it. We can't seem to get it to work properly. But conversely, if you accelerate upward, so if you're going upward in an elevator, your normal force is going to be greater than your weight. So your actual weight on the scale is going to read more than what your actual weight is. But if you accelerate down, it's going to read less than what your actual weight is. And there's the math to prove that. So B, what does the scale read when the elevator descends at a constant speed? So not to get too mathy on this, net force is MA. Net force is normal force minus 637 equals 65. But if I'm moving at a constant speed, my acceleration is 0. So 65 times 0 is 0. So Fn minus 637 equals 0, which means Fn is equal to 637. So if you're not accelerating in either direction, if you're going at a constant speed, these should be equal because there's no acceleration.